The Moivre's theorem is basically one of the can say the application of the Euler form of a complex number, but it has a more we can say um, more generalized way of finding the root of any complex number. Okay, so let's talk about the this Moivre's formula. Basically, we call it Moivre's formula. So let's say any cos theta plus I sin theta to the power n. This is depending on n, it has two values. This is cos of n theta plus I sin n theta. Okay, this n is the argument. This is possible if n is integer. If n is not integer, then so if n is something all real values except the integer. If n is not a integer but all real values. See, by the way, n is real values. Again, I am emphasizing, if n is complex, then it will be totally different. Then Moivre's theorem will not be applicable. So if n is basically a real number, n is a real number. So if n is an integer, then we can directly say that the cos n theta plus I sin theta. But if n is not a integer, all real number except integer, then one of the value is cos. So I can say one of the, so one value is cos n theta plus I sin n theta, and other values also, and more values. Okay, so it's not that one of the value, if n is not integer, then one of the values cos n theta plus I sin theta, whereas if n is integer, then only value is cos theta plus I sin theta. So in short form, sometime we write like this: cis theta to the power n is equal to cis, this is cis, the short form of cis n theta when n is belongs to integer, and cis n theta is one of the values, and other more, and more values, and more values when n is all real values except integer. Okay, and see, this is we can in a crude way we can observe that if we apply the, let's say, Euler forms, e to the power I theta n is nothing but e to the power I n theta. So we can clearly see it's a crude way of proof the why the cos theta plus I sin theta to the power n is cos n theta plus I sin n theta. Okay, so basically what I mean to say that, let's say if I say cos, or let's say directly write Euler form, e to the power I theta to the power 2, this is e to the power I 2 theta when this is only one value. Okay, only value, and this is obvious, okay, it's obvious. But if I say, let's say, e to the power I theta to the power okay, let's make it 2 I to the power I theta to the power, let's say, 2 by 3, this is nothing but e to the power I 2 by 3 theta. Now this is one of the values, is one of the values. There will be other 3 values possible, but this is the one of the values. Okay, so see, in case of let's say if I say any real number, let's say we discuss x square is equal to 4, where x is something a real value. So if I say what is x is equal to root of plus minus root of 4, that is plus minus 2. Got it? So here if someone say what is x of root 4, this is only value 2. Okay, will not say x is equal to root 4 is plus minus 2. There is only one value 2 is possible. So when x is real, then in case of polynomial we have done in the grade 8 or 9th, where we say x is equal to root 4, then it's only value 2. if x is equal to root 4 does not have minus 2 also, because this is absolute value, this is always positive value, it will never give the negative value. Okay, but when it comes to the complex number, then some more general things happen. So let's see we see the nth root of okay, so well, let's see the nth root of unity. This is one of the application of de Moivre's theorem to finding the nth root of unity. So let's say we have any complex number, let's say z is equals to this also, let's say power 1 by n. This is also a complex number, so this is also a complex number. So we are finding the nth root of any complex number, that will also be some complex number. So this is rho is also a complex number, and obviously here n is natural number. We are talking about the nth root of unity. Okay, so that's why n is a natural number. So if I have to find the nth root of unity, what we'll do, we will take the z to the power n is equal to rho. Okay, so obviously here rho is known, we have to find the z. That means, for example, I have to find the what is the, let's say 2 plus I 1 by n. We have to find the, or let's say 1 by 4 or 5. We have to find the fifth root of complex. Achha, by the way, we'll change, it's not unity, we'll see the complex number. Okay, so we're talking about the nth root of complex numbers. So any complex number, we have to find the fifth root. So we'll see how to find the nth root of any complex number. So essentially what we do, z is equal to 2 plus I to the power 1. So what is the z to the power 5 is 2 plus I. So essentially z is unknown. This is the unknown number. Z is unknown. We have to find the z, and we need to find this z. Okay, so how we'll find, we'll see one by one. So let's say we have z is unknown, and that is rho to the power 1 by n. What we do, we converted into z to the power n is equal to rho. See, z and rho both are complex number. See, z and rho both are complex number. Both are complex number. So we convert into the, let's say, some Euler form. So this is mod z, the modulus e to the power I theta to the power n, and rho also convert into Euler form, that is the modulus of rho e to the power, let's say, I alpha. Okay, clearly for rho the modulus is rho and the argument is alpha, and for z the modulus is mod z and the argument is theta. Okay, both are complex number. So now we will use the de Moivre's theorem. So using de Moivre's theorem, using basically it's a, we call it de Moivre's formula. Only use small d, de Moivre's formula. We call it theorem most of the book, but essentially it's de Moivre's formula. So using de Moivre's formula, we can get this zn e to the power I and theta is equal to rho e to the power I alpha. Okay. So essentially e to the power I alpha, see, if you observe what is e to the power I alpha. So e to the power I alpha is e to the power I alpha is cos alpha plus I sin alpha. But since cos and sin are a periodic function with periodicity 2 pi, we can also write it like this: cos of 2n pi plus alpha plus I sin 2n pi plus alpha. Okay, let's say I zoom it here. Okay, fine. So essentially what we can write, we can write the mod of z to the power n e to the power I and theta is equal to mod of e to the power I alpha, and we discussed that e to the power I alpha is same as we can say it's same as cos of alpha plus I sin alpha. So I can write, being a periodic function, cos of 2k, we use k pi plus alpha plus I sin 2k pi plus alpha. So that means, since this is there, okay, so we can write this as same as rho e to the power I alpha plus 2k pi. Okay, so so basically, and obviously k is integer, so I can write this particular form in this form. So mod z e to the power I, and theta is nothing but rho e to the power I 2k pi plus alpha. Clearly here n is already integer, it's a given. Okay, it's given that nth root of unity, whereas k is also a integer. Okay, which because it's a periodic function, so cos is periodic function, so its periodicity is 2 pi, so it can be any integral multiple of 2 pi is the periodicity of function, with the fundamental period is 2 pi. Got it? Okay, now we'll again what we'll do, we can simplify this part. So I can say that the these things, mod z and these are equivalent, this part, they are same. First, their modulus is same and their argument is also same. So I can say and n theta is equals to 2k pi plus alpha, or theta is 2k pi plus alpha by n. Okay, where k is integer. Okay, k can have infinite values, so it's a periodicity. This is a periodic value. So periodic means alpha plus 2 pi, alpha plus 4 pi, alpha plus 6 pi. There are infinite values of k are possible. So here k is integer, and obviously k will have a infinite values. K will have a infinite values. Got it? So essentially we end up with this form. Mod z is equal to, is fine, there is no much thing. The important thing is this one, theta is equal to 2k pi plus alpha by n. Okay, that is the important formula. Obviously k is integer, there are infinite values of k possible, but being cos, there will be sometime repetition. See, if I say cos of 2k pi plus alpha by n, okay, after some time the repetition of the values will occur, so no need to write again and again. So when does the repetition occur? So the repetition of values occur, in this case the repetition occurs. When does the repetition occur? Repetition occur for k is equal to n onward. Okay, that means if k is equal to 0, I have cos alpha by n. Okay, so k 0, 1, 2 up to n minus 1 distinct values. Then after k is equal to 1, again we will get the same values. Repetition will occur. Okay, you can see why it is happening. See, the thing is, cos of, let's say, 2k pi plus alpha by n. Okay, if I, let's say, choose k is equal to 0, then this value is cos alpha by n is distinct values. If k is equal to 1, cos of 2 pi plus alpha by n is also distinct value. But if I choose k is equal to n minus 1, again that is a distinct value. 2 k is n minus 1, so 2 n minus 1 pi plus alpha by n. Okay, but if I choose k is equals to n, so what happens? K is equal to n, that means cos of 2n pi plus alpha by n. That is nothing but cos of n cancelled out, so 2 pi plus alpha by n. Got it? So essentially this value is same as this value. Can you see here? So this value k0 cos alpha by n, and k is equal to n cos 2 pi plus alpha by n is nothing but cos of alpha by n. Okay. So essentially after k is equal to n plus 1, the repetition will occur. Got it? So that's why we will only take the theta values will be 2k pi plus alpha by n, where the k values is obviously integer will lie from 0, 1, 2, 3 up to n minus 1. We'll only consider up to, there are n values. There are nth root of unity, so there will be n such values will be there. Got it? So this is how we find the nth root of unity. So we can check it. So when k is equal to 0, theta is alpha by n. When k is equal to 1, theta is 2 pi by n plus alpha by n. When k is equals to 2, theta is or let's say directly jump to n minus 1. K is n minus 1, theta is alpha by n plus 2 pi by n minus 1. When k is equals to n, then theta will be alpha by n plus 2 pi n by n, and cancel out. So I will get the 2 pi plus alpha by n. So it is essentially nothing but the alpha by n as we discussed. Similarly, if we take k is equal to n plus 1, theta is equals to 2 pi n plus 1 by n plus alpha by n, that nothing but 2 pi plus 2 pi plus 2 pi by n plus alpha by n. This is nothing but the 2 pi by n plus alpha by n. Okay, this same. See, the k0 is alpha by n and kn is also alpha by n. Similarly, k is equal to 1, 2 pi by n plus alpha by n. So 2 pi by n plus alpha by n. So after 0 to n minus 1 are distinct values, and after that repetition will occur. Got it? So comes to the original problem. The problem was to find the nth root of any complex number. So our problem was to find, let's say z is equal to 1 by n, where n is integer. Okay. Since we are talking the nth root, fourth root, fifth root, so let's say n is natural number. So we'll get the z to the power n is equal to rho. Essentially we have the two parts. One is mod z is equal to mod rho, and theta is equals to 2k pi by n plus alpha, where k values will be 1, 2, 3 up to n minus 1. Clearly, what is alpha here? Alpha is the argument, of complex number z. So finally we get z. Our known was z, no? So here we have to find the nth root of rho, complex number rho. So rho is known, but z is unknown. So what is z now? So z we can find have this value, rho 1 by n e to the power 2k pi plus alpha by n, where k values is 0, 1, 2 up to n minus 1. Here we get n values. So essentially we get n values, because for k is 0 to n there are n values. So we get n values of z. We get n values of nth root of complex number rho. Okay, we get n values of z. And why it is happening, we can also see, since we are solving z to the power is equal to 1 by rho, so it's a n degree polynomial, and therefore we have n solutions exist, n solution is possible. Okay, so essentially we have, this is a very important formula of nth root of any complex number. These things we'll substitute these values, and we will take up to value from 0 to n minus 1. Okay, now there are some properties of this nth root of complex number. So essentially we'll see the properties of this nth root of complex number. There are many properties. So first property is we can say the roots. The roots lie on a circle with center origin. Yeah. So basically the roots lies on circle with center origin and radius moderate 1 by n. Okay, so essentially since we are talking about what is z is nothing but so z is nothing but, okay, we can say, let's say 1 by n. So to find the locus we take modulus both sides. So mod z is equal to mod rho 1 by n. So since rho is a complex number which is given, this is a constant, this is a constant, this is the constant. So this is same as the, and z is variable. So this is same as the, we recall that z minus z naught is equal to rho, the constant, the real number. This is a real number. So essentially this represent a locus of a complex number with z naught as the center, radius r. So same here. So if we talk about this particular form, we taking the modulus. So taking modulus, we are able to know the locus of z. So locus of z is a complex number. So essentially what happens, so we have the just a minute. So basically it will have a it will have a complex number with center as the origin. So basically this is the axis. So the z lies on the, and this radius, the radius of this particular circle is rho 1 by n, and whatever the roots, let's say roots are z1, z2, z3, z4 up to zn. N roots means zn roots. Okay, zn roots, because k is equal to 0 represent the first root, k is equal to 1 0 represent the second root, and similarly k is equal to n minus 1 represent the nth root. Okay, so there are 1 2 3 4 n roots, they all lie on the circumference of a circle. This is the first property. And let's talk about the second property. Second property is that the roots, if you talk about the roots, the roots are in the, okay, what are the roots? If you talk about the roots, so roots are z is equal to rho 1 by n e to the power I 2n pi plus alpha by n, or I can say this nothing but 1 by n e to the power I k. This is this one. Okay, so this is the roots. So basically the roots lie on the, we can say that the important thing is roots are in GP. Roots are in geometrical progression with common ratio, as e to the power I 2 pi by n. Okay, we can check it by, see what is the first root for k, putting k is equal to 0. The first root is rho 1 by n e to the power I alpha by n. What is second root? K is equal to 1, that is second root is equal to rho 1 by n e to the power I 2 pi by n plus alpha by n. This is nothing but rho 1 by n e to the power I 2 pi by n into e to the power I alpha by n. If we take the k is equals to 2, the third root is rho 1 by n e to the power I to 4 pi. 4 pi by n plus alpha by n, this is nothing but 1 by rho 1 by n e to the power I 4 pi by n e to the power I alpha by n. So and so on. So essentially, if we talk about the these are the roots z1 z2, they are in the, these values are in the geometric progression, geometric series. We can check. See, how do you know the geometric progression? The we can say the second root upon the first values up, it should be equal to third upon second, and they are the common ratio. So here we can check what are these values. So what is z2 by z1? So z2 by z1 is the cancel out, we get e to the power I alpha by n. Similarly, what is z3 by z2? z3 by z2 is e to the power I 4 pi by n e to the power I 4 pi by n into e to the power I alpha by n divided by e to the power I 2 pi by n into e to the power I alpha by n. So essentially alpha 1 cancel out, to get I 2 pi by n. Sorry, here also the z2 by z1 will be the cancel out, I will get e to the power I 2 pi by n, and they are nothing but the common ratio. So they are the common ratio. Okay, since this what is this value? This is z2 by z1, and what is this value? This is z3 by z2. Since z2 by z1 is equal to z3 by z2, hence they are in geometric series, and corresponding ratio is the common ratio. So the common ratio is e to the power 2 pi by n. Okay. Now the third property is if we join the roots, joining roots by segment will form a n-sided regular polygon. N-sided regular polygon. What does it mean? So essentially, we know that the roots z1, z2, z3 lies on a circle with so this is with the center as the origin. z1, z2, all the roots will lie, let's say this is the z1, this is z2. So what is z1? We have discussed here. The z1 is e to the power I alpha by n, and z2 is e to the power I 2 pi by n into e to the power alpha by n. So essentially, so by the way, the radius of this particular circle will be 1 by n. And what is z1? z1 is e to the power I alpha by n. So this angle argument is alpha by n. Then z2 is is also multiplied 1 by n. So z2 is 1 by rho 1 by n e to the power I 2 pi by n plus alpha by n. Okay. So the argument will be e to the power alpha plus 2 pi. So this is 2 pi by n. Similarly, somewhere is the z3. Again, this is also a 2 pi by n. Somewhere is, let's say, z4. This again a 2 pi by n. Okay. So all the angles are equidistant. So if we join these roots, so let's say this let's say if we join this root, so we'll get this one, this line segment, then z1 z2 z2 z3 z3 z4 and so on. Okay, and so on, z3 z4 and so on, something like this. Got it? So they are forming a regular polygon. So essentially, if we draw a bigger picture, Okay. This is Z1, Z2, Z3, Z4. This is alpha by n, but all other angles, this angle is also 2 pi by n. This is also 2 pi by n. This is also 2 pi by n. Okay. So since in we know that any regular polygon, okay, if any regular polygon, if we join the vertices with the center, okay, the angle between the angle which is subtended by each sides are same. This is, let's say, theta, this is 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 theta. Since angle subtended is same, hence they form a regular polygon. Got it? So essentially here it's a regular polygon. So any we go, let's say this Z1 and somewhere it's Znth, somewhere is Znth. So what is the Znth? In general I can write nth root is rho 1 by n e to the power I 2k pi plus alpha by n. Okay. Okay. And one more thing, last thing is it's you can check it. The in case of the you can say a fourth property or this observation, this is not the property but the observation. Its observation is there. Its observation is that the minimum number of imaginary roots. You can check it. The minimum number of imaginary roots is equal to n minus 2 and for example obviously there are n roots, so if there are n roots, so n minus 2 are imaginary roots, so remaining are the real roots. For example, if we take the cube root of unity, okay, let's say z is equal to cube root of unity. So in this case we'll see in detail next time, but just want to show that this has a one, what are root possible values. Z1 is 1, so if you solve using the method I explained, so Z1 is equal to 1, Z2 will be omega is let's say minus 1 plus root 3 I by 2, and the third root is omega square, that is nothing but minus 1 minus root 3 I by 2. Okay. So here we have two imaginary roots. Minimum number of imaginary roots is n minus 2. So n is 3. So n minus 2 is 1. So minimum 1 should be there. Maximum possible, but minimum 1. So we say that we have minimum 1 imaginary roots is there. Got it? That is just observation. So next time we will see the cube root of unity. That is very versatile. So most of the books deal with the cube root of unity. But the cube root of unity is nothing new. It's something you can the procedure by the process which I have explained here, finding the cube root of unity, cube root of any complex number. Just consider the row as a 1, then you get the cube root of unity. The process is exactly same. Okay. So next time we'll see the cube root of unity.